So in section 2.3, we're going to be looking at the relationship between limits of functions and the algebraic operations. And we did something similar in chapter 1. And in fact, I highly recommend, if you haven't already done so, watch section 1.3 on how algebraic operations uh, have a relationship with sequences, because this chapter is going to be using a lot of the same proof techniques. And it really is just basically the same section, I should say, but now we're dealing with limits, not just with sequences. So, with a definition, and here it's not really a definition of the word, it's just we're defining what f plus g is if f and g are from d to r, are functions that map from d to r. Well, then f plus g of x is f of x plus g of x. That's how we're defining it. Same thing with the product. F times g of x is the same thing as f of x times g of x. And finally, as long as g of x is not 0, f over g is defined by f over g of x is equal to f of x over g of x. Yeah, so now we can, we have the three theorems. So I'll go one by one. So suppose f and g map d to r with x not an accumulation point of d. And further suppose that f and g have limits at x naught, then f plus g has a limit at x naught, and that limit here, as x goes to x naught of f of g, f plus g of x, is the limit of f of x as x goes to x naught plus the limit of g of x as x goes to x naught. So kind of intuitively, you should, I shouldn't say intuitively, but from calculus, you should probably just kind of already be thinking, oh yeah, well, I remember this to be true. Same thing with the product. F times g has a limit at x naught, and that limit happens to be the two limits multiplied. And this, as you can probably imagine, as we defined up here in green, the three operations, we now have division. So if g of x is not equal to 0 for all x and d, and the limit is not equal to 0, then f over g has a limit at x naught, and that happens to be, again, the limit of f as x goes to x naught over the limit of g as x goes to x naught. And we're going to prove these. Now, for these, the proofs of the first one and the third one, so this one and this one, will be accomplished by the use of sequences, right? Whereas we're going to prove 2 directly. And 2 might be a bit, I shouldn't say more complicated, but just different. So I guess we'll start now with the first one. And before we do, we're going to need a lemma. This lemma we've already seen before, again from section 1.3, that says if a sub n converges to a and b sub n converges to b, then the sum of the sequences converges to the sum of their limit points. Right? So for the proof, not too long, we're going to let x sub n be any sequence of points in D converging to x naught, with xn not equal to x naught for all n. Well, then we need to show, or it suffices to show, that f plus g of the sequence xn converges to limit of f of x plus limit of g of x as x goes to x naught. So by assumption, f and g have limits, right? Our assumption, let me erase here so I can show you where our assumption was. Over here, up here, suppose that f and g have limits at x naught. So that's where we're getting at. So by assumption, they have limits at x naught. Hence, f of x n converges to limit of x as x goes to x naught. And similarly for G, this converges to this. Well, by the lemma below, we have that our theorem holds true. Right, and remember we showed this here. We can use from the theorem we used, or we proved in last section, right, where we showed that f of xn converges, and well, it has a limit point. So again, we're using, like I said, for 1 and 3, just as we did here, we're using the use of sequences. We're using sequences. So this one's fairly straightforward. The second one, however, might not be. So first, again, we're going to need a lemma, but this one is a lemma that we saw from last section. This lemma says let f map d to r with x not be an accumulation point of d. If x has a limit point, if f has a limit point at x naught, then there's a neighborhood q of x naught and a number m, such that if x is in the intersection of q and d, this function is bounded by m. Right, so our theorem, as we had seen before, that's number 2 from the last slide. How do we prove this? Well, first, given epsilon greater than 0, we must find an appropriate delta greater than 0. Right, because we're dealing with limits. And as I wrote here, as the plan unfolds for finding delta, you should really observe the parallel between this search for n and the one in the theorem in section 1.3. So like I said, look at the operation there for multiplication with the whole sequences, the property of sequences where you're multiplying two sequences with each other. It is going to be really similar. So first, choose an epsilon greater than 0. And we're going to denote a as a limit of f of x and b as the limit of g of x. Well, like it says here, we wish to find a delta greater than 0 such that given this, if this, then this is less than epsilon, right? Because we want to show that this product, the difference between the product and their limit points is less than epsilon. Right, that's just come from the definition of limits. So, by the lemma above, there's a delta sub 1 greater than 0 and a real number m such that f of x is bounded. So we're going to let epsilon be, I suppose prime is equal to this epsilon over absolute value of b plus m. Again, if this choice of epsilon isn't quite clear, again, I recommend going back to section 1.3, viewing that lecture again and see how we work out or how we choose our appropriate epsilon. So let epsilon prime equal epsilon over absolute value of b plus m greater than 0. Well, there's a delta 2 greater than 0 such that if this holds, this inequality holds, then f of x minus a is less than epsilon prime. And there's a delta 3 greater than 0 such that, again, if this holds, then the same holds for g of x minus b, right? It's less than epsilon prime. Again, here may not be so clear. You might want to work out the details within this proof And I mean, like I said, they've been done in section 1.3. But now we're going to let delta be the minimum of all these deltas. So delta 1. So let me just erase here. Delta 1 is up here. Delta 2 for f is this one. And delta 3 is this one. Well, now, if delta is greater than x minus x naught, well then, f of g of x, not the product f times g of x minus ab, and again, just a reminder, a and b are up here. That's the limit of f of x and g of x respectively. Well, that's just equal to f of x times g of x minus ab. And that, here's where we use our little add zero triangle inequality trick. That's less than or equal to this here. Again, we added 0 and then triangle inequality. That's why we have the inequality. That's just equal to f of x times g of x minus b plus b times f of x minus a. That's less than m. So again, here, this is greater than or equal to f of x, right? Because f of x is bounded. This here is less than epsilon prime. This here we know is, well, it's a limit point. So, I mean, it's just, we know it's not infinity. And this here is less than epsilon prime. That's why we have this inequality, strict inequality. And that is just equal to epsilon. Again, if you do the algebra, plug in epsilon prime, this epsilon prime over here, plug it into that, that'll give you epsilon after you do the whole algebra. Showing what? That this is less than epsilon, which means that our theorem holds. And really, the only tricky part in this is maybe the only clever part is maybe somewhere here where actually it shouldn't be that. It should be our choice of epsilon prime. But like I said, section 1.3. Everything else pretty much follows from stuff we already know. We're just applying it to limits. So we can to our last theorem. And our last theorem, like the theorems before, we're going to use a lemma. And this one, I mean, we used it in the proof for the first one too. But this one we saw in section, actually in the last section, 2.2. So it says let f map d to r with x naught an accumulation point of d. Then f has a limit at x naught if and only if for each sequence x of n converging to x naught with xn in d and xn not x naught for all n, the sequence f of xn converges. Right, so it's just kind of saying like the whole limit thing, how the closer we get to x naught, the closer our function values get to L. And again, that was the theorem from last section. But now we can use this to prove our theorem, the third theorem. And I won't repeat it because we already went over it, but we're basically trying to prove this. So it's a shorter proof. Suppose xn is a sequence members of D, distinct from x naught, converging to x naught. Now f of xn converges to limit of f of x and g of xn converges to the limit of g of x. Right, and that's because our assumption that f and g have limits at x naught. And our little lemma. Well, since g of x is not equal to 0 for all x and d, well, we can guarantee that g of xn is not equal to 0 for all n. By assumption, again, we're assuming this assumption is up here. If g of x is not equal to 0, and limit, so this assumption is here, is not equal to 0. Well, by assumption, it's not equal to 0. Therefore, what can we do? Well, this here, we know is equal to this. Which converges to the limit of f over g as x goes to x naught. And by our lemma, f over g has the indicated limit, this here, at x naught. So this one really is, I remember, I think when I first read it, I was like, wait, that's it? It's that simple? And really there isn't much to it. Using this sequence and the sequences and this lemma up here makes our life really easy. Okay, now I'm going to present a corollary, which I won't be proving. You can try the proof as an exercise. Not sure if it's in the book, might be in the book, but try not to peek, try it on your own, and then you can peek at the solutions. But it says, suppose f and g map d to r, x naught is an accumulation point of d, and f and g have limits at x naught. Well, if f of x is less than or equal to g of x for all x, well, then the limit of f is less than or equal to the limit of g. And again, this should be pretty intuitive. And again, since we're following the same structure of section 1.3, we move on to some theorem that's quite interesting. So remember, actually I should bring up the picture first. So remember that sine 1 over x failed to have a limit at 0? Right, so because it looked something like, and then it oscillated incredibly quickly close to 0. Well, so because it fails to have a limit at 0, we can't use a previous theorem. The second theorem we looked at, the f times g is equal to the product of the limits. But we do know that sine x is bounded. And it's bounded by what? By -1 and 1. So because of this, we can now guarantee that x times sine 1 over x is less than or equal to absolute value of x. Right, because of that boundedness. Well, therefore, f has a limit at 0. And in fact, the limit is 0. Oh, you can't see it there. I'm going to erase here. The limit is 0. So remember with sequences where you have a bounded sequence, and then a sequence that converged to 0, well then the product of the sequences converged to 0. And it's going to be the same reasoning here. So our theorem says that let f and g map D to R and x naught be an accumulation point of D. If f is bounded in a neighborhood of x naught and g has a limit 0 at x naught, then their product has a limit at x naught, which is 0. Again, one is bounded, f is bounded here, and the other has a limit at x, has limit 0 at x naught. So how do we prove this? Really similar to how we did last time. Choose epsilon greater than 0. There's a delta 1 and m greater than 0 such that f of x is bounded for delta 1 greater than x minus x naught. We're going to let epsilon prime be equal to epsilon over m. And if you're just seeing this section, the choices of epsilon prime or epsilon are a bit clever. You should definitely review section 1 first, all of chapter 1 first. It's just pretty much doing some scratch work, figuring out some algebra. But we're going to let epsilon prime equal to epsilon over m. So there's a delta 2, such that if delta 2 is greater than x minus x naught, and that's greater than 0, well then g of x minus the limit of g of x is equal to g of x. And why is that the case? Well, because this has a limit, what? Has a limit 0 up here. All right, so that's just g of x. And that's less than epsilon prime. Again, because of the fact that g of x has a limit at x naught. Well, now, when I choose delta to be the minimum of delta 1 and delta 2, why? Well, so we can guarantee that if delta is greater than x minus x naught, then our computation, the product, same thing as f of x times g of x. Again, another property we already know. That's equal to the absolute value of f of x times the absolute value of g of x. That's less than or equal to m times epsilon prime. And well, that is equal to epsilon. What does that tell us? Well, that just tells us that the product has a limit at x naught, and that limit is equal to 0. And we have one more slide to go, and it's probably the most interesting. I apologize for going a bit fast in this section. It's really because I expect you guys to already know section 1.3. All right, I hope you guys have worked out problems. So these concepts, nothing here should really be new. It's just other properties of limits. And so probably my favorite, it's a bit interesting. So here I just have a polynomial. We're not going to be working with this polynomial specifically. It's just that equation. But we are going to be talking about polynomials. So, and this is not a proof. This is not a theorem. This is just kind of information. That's why it's a black box. No pun intended. So suppose f maps R to R. And suppose that function is defined as f of x equals to x, right? For all x, for all. So we know how that looks, right? That little function. I should draw it over here. That function looks like, oh, it passes through the origin. I should draw it here. With slope 1. Anyway, if x is in x naught is in R, then we're just basically using a theorem from before, from last section. that if xn converges to x naught, with all xn not being equal to x naught, well then f of xn is equal to x sub n. So f has a limit at x naught, right? And in particular, f of x is just equal to x naught. Right, so nothing too fancy. But now choose k and consider the function where g of x is equal to k for all x. Right, so k is just a constant. Well, then g has a limit at x naught, and that limit is always just k. Right? And the reason I'm saying this is because now we go into the interesting part. So that's just kind of regurgitating what I just said, what's up here. But by the use of induction, and 2, remember the product of the functions where they have a limit is equal to, they have the limit is the product of the 2 limits of the functions. So by induction and number 2, we see that f of x is equal to xn has a limit at x naught, right? And that's because x times x is equal to x squared, right? X times x dot 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 x n times, we get this, right? We're using the second theorem, the product, to show that the limit of x to the n is equal to x naught to the n. Right, so what is that saying? That says that the polynomial x to the n, I should say it's a monomial, has a limit exactly where you'd expect it to. And again, using this result and induction on parts 1 and 2. Again, if you don't remember what parts 1, 2, and 3 were, look at the second slide. But we find that every polynomial has a limit at exactly the place you'd expect it to have a limit. So for example, if you look down at the picture, the limit at x0, just plug in 0 to the x's and it's you'll get your result. Right, it should be -1 when of x is 0. That's why x is here is -1. Right, so this is just basically saying polynomials have a limit at exactly where you think they do. And we saw this in calculus class, calculus 1, but we didn't really see why. It's just kind of like, oh, it just happens to be like that. And the last thing is if p and q are polynomials and r1 to rn are real roots of the equation, qx is equal to 0. So here, let's just say this is equal to q of x. Okay, we have 1, 2, 3, 4, 5 roots, right? So we have r1, r2, r4, and r5. R1, R5, R4, R3, R2, 2. So this here, I should color code stuff. Let me erase this. This here is this. Well then, for f being the real numbers, not counting these roots, not counting these roots, defined by f of x is equal to p of x over q of x. It has a limit at every point of x naught. And that limit is also exactly what you'd expect it to be. And you might be wondering, what about the existence of the limit at these points, the roots? What about the existence of limits at that point? Well, that we're going to handle it differently. I guess we'll just I should say we're going to postpone it till now, because we're going to have to discuss continuity for that, which is actually the next chapter coming up. So you shouldn't wait too long. But we're going to see that property and well, some other properties as well. Like if you've done exercises, you should know that the sequence a sub n converges to square root of a. And we can use that result to this chapter to show that the square root of f of x, well, if f is greater than 0, has a limit at x naught. And that limit is also exactly what you'd expect it to be. But again, more discussion about limits will appear in later chapters. And we're actually just going to end this chapter with the next section 2.4. And it really is just one theorem we're going to look over. It's two because we use a lemma, but it's one big theorem we're going to look at, and then we can move on to continuity.